quite brief run through minimal model program for threefolds. So this is the Murray theory, and the main reason for giving it is to explain the question, to answer the question why at Q finite. Right, so maybe some of you think, maybe some of you are happy with ordinary non-singular finite threefolds and think, you know, you don't need to go any further. So let me just say what the minimal model program for threefolds is, because it generalizes the minimal model program for surfaces that most of you know perfectly well. So given any x, I can, you know, for example, non-singular projective, I can do this, I can do a program like this, which ends up with some xn, so this is x prime, and so these are birational transformations. So they're the analogues of contracting -1 curves on a surface to make it more minimal, closer to being minimal, and at the end, either kx primed is nef, and then you go on to study this and you find that the Kadara dimension is greater than or equal to 0, yes, or x primed has another structure, has a Murray fiber space structure. Right, so Murray fiber space means x primed maps to S with some properties. So the dimension of S is strictly less than 3. So it could be 0 or 1 or 2. And minus kx primed is ample, relatively ample. Yes? So if S is a surface, this is a fiber space of generically curves on which minus k is ample. So that this means it's a fiber space of curves that are birational to P1, right? And so this is so x prime to S is conic bundle if dimension S equals 2, or it's a family of Del Pezzo surfaces, you know, possibly P2, but possibly some other Del Pezzo surface. If dimension S equals 1, and if dimension S equals 0, it means that, or S is a point, and then this condition that minus k is relatively ample says that x primed is minus kx primed itself is ample. Right, so this means that S is spec of a field, in my case spec C, and minus kx is, so that means that it's a Fano variety over C. Yes? However, the point is that this only works if you allow some singularities. So even if I start with something which is singular, the very first step of this might be contraction to something which is singular. And you can't avoid this. You can't run this program in anything other. You must have a singular category. So terminal singularities are the smallest category where this works. Yes. So when you do, there's possibly the biggest distinction between the surface case and the higher dimensional case. If you think your surface is not minimal, you look around the surface to find a -1 curve. And a -1 curve is a geometric locus. In Murray theory, that's not what you do. People tried to do that in the 60s and 70s when I was first on the scene, and it just doesn't work. It just leads to impossible problems. So Murray's big invention is to work in this with this cone of curves, and the thing you contract is an extremal ray of the cone of curves. So in other words, it's a homology class. You look around the manifold, and you're not looking for a geometric locus. You're looking for some homology class that contains curves, and so that it's extremal. So that if you, and then you can find a divisor, which is a supporting hypersurface of the divisor. And you can use this divisor to make a contraction. So a priori, you don't know what you're going to contract. You might be contracting a divisor to a point, or you might be contracting 50 homologous curves to a point, a finite set of homologous curves to a point, or you might be contracting the whole variety to a surface, or a whole variety to a point. Yes? And you don't have the choice. You're running a program, and the homology in this Murray cone forces you to choose one of the extremal rays, and only after that you do a classification of extremal rays, and you find out what it is you've contracted, right? So terminal singularities. Let me just say the definition. So it means that RKX is locally. This is a definition in singularity theory, so it's local as a point. So I write P in X to mean a germ of X at a point. So I want this to be a Cartier divisor, and I want when I do Y to X resolution of singularities. So the resolution of singularities pulls out an exceptional locus, which is a union of divisors. Yes? And so then I can write, because this is Cartier, I can write F upper star of Kx. So by definition, remember, this is F upper star of RKX, pull back of a Cartier divisor, and then I divide by R. And so I can write Ky is F upper star Kx, and I can these are both divisors now on a non-singular variety, so I can ask for the difference of them, and this is plus sigma AI EI. So I could write this for any isolated singularity, which is Q Cartier, yes? But the terminal condition is that this AI should be greater than 0. All AIs for all the exceptional divisors. Yes? And so, there are other categories of singular, you can, down to log canonical, where you demand that the AI is greater than -1, or even greater than equal to -1. But this is the smallest category, right? And these singularities are more or less tractable. So terminal singularities are threefold. So they're either, so there's hypersurface singularities, hypersurface compound Duval singularities. So this means I write down, you know, in C4 with coordinates x, y, z, t, I write down f of x, y, z. So this is one of these Duval polynomials. Right, the things that define the rational double points, or the Duval singularities, plus t times g, and g of x, y, z, t. Yes. So when I take the hyperplane section t equals 0, I get a Duval singularity, and it's supposed to be isolated. Yes, and so that. But this f can be, you know, even if you fix this t can be a lot of things. So, you know, this is not in any sense finite dimensional, but it is tractable. You can work with it directly just using this, this form, right? And so there's a quotient singularity. So the orbifold points, 1 over r, 1 a r minus a, and here coprime. Yeah, so that's why I keep on about these orbifold points, and then there's a kind of mixed case. There's a hyperquotient. So this, you know, there's a list here which is due to Murray, and which is explained in detail in my paper, Young Person's Guide. I think I have a copy of it. Either I have a copy of it here, or I have a copy of it here. So there's a list of 6 cases, and the big case is, you know, corresponding to the you know, type A singularities or type A root systems is, it looks like this. I write down x, y equals f of z and t, and then I want to divide this out by a group action, which is 1 over r, 1 minus 1, b 0. Yeah, and so, you know, this is x, y, z, t. The x and y have these opposite signs. Yes, and that means that this is invariant. So I want this polynomial to be invariant. The b is supposed to be coprime, so I have to put z to the power of r there. Yes, so from the point of view of this is supposed to be, this isn't. What this is an isolated curve singularity with mu r action. Right? After I've set x and y equals 0, I'm seeing this kind of orbifold behavior where there's only 2 variables, z and t. There's an isolated singularity in z and t, but it's supposed to be in the z can only appear as z to the power of r. Yeah, and so you know, this is still you know, this is still a big class of singularities. It's essentially all plane curve singularities, all isolated plane curve singularities. But you know, we think of this as tractable, and you know, the thing that's tractable is that if I take an unfolding of this, I get rid of the singularities altogether, and I just get a pile of these things. Yeah. So this thing here is the same thing as a minus a1. Right. Just changing roots of unity. Just changing the basis for this group of roots of unity. These are the same group action. Yes. And so if I just if I move this sideways a little bit, if I do a deformation of it, then so deforms two orbifold points. Right. So this is called a Q smoothing. Yes. And so this is locally. This is proved in Young Person's Guide, and also globally. So this is proved globally on Fano threefolds, on Fanos. This is the thesis of Taro Sano. So, you know, I'm slightly oversimplifying, but yes. So that means that when I'm looking, if I'm looking at a Fano threefold, you know, for example, if I want to prove that some Fano threefolds exist, then if they exist, then they will have a small deformation which has only these orbifold singularities. Yes, and so the game I've been telling you of playing in looking for fixing a genus and fixing a basket of singularities, this will give us all Fanos that exist. Yes. So, you know, if you think about everything that you want to do with minimal models of surfaces, you start off with any old surface, you push it down and down and down by contracting -1 curves, and at the end you get either P2 or one of the scrolls. Yes? So here you do the same thing, and at the end you get this X primed, and these X primes form these huge moduli spaces, conic bundles, you know, and they have some rigidity properties. So I'll talk about that a little bit tomorrow. So, you know, if you want to be able to play the games with threefolds that we like playing with surfaces, you don't have any choice, but you have to work with the output of the minimal model program, which are all these things. So these also have, you know, these terminal singularities, and you can't avoid it. You can't. There isn't anything simpler. Okay, so that's the why. That's asking the question of why we're doing Fano threefolds. So the next thing I want to talk about is this idea of unprojection. So there's a theorem, but, you know, as usual in my habit, I'll start off with an example. So everybody knows this setup. S3 in P3, a cubic surface containing a line. Yes? So I can contract this line to a point, and having done that, I will have a del Pezzo surface of degree 4. Yes? So let's do that in a kind of slightly algebraic way. So it means that the equation of S3 is, so let me write it in a x times b minus y times a. Yes? I'm just writing any cubic equation. So this is x, y, z, t, and this is x equals y equals 0. I'm just writing down any cubic form that's in the ideal of x and y. Yes? And so when I do this, it's written down so that if I write S, a over x, b over y, this is a form of degree 1. It's on S, it's well defined because of this equation, and it's got poles along L. Yes, and so I can make, instead of the linear system O of 1, given by x, y, z, and t, I can use O1 together with this L. So I can use O of 1, I can use H, O of 1 in P3 plus L, gives a new linear system, x, y, z, t, and s. Yes, and that maps me to t in P4. And also we know the equations. So, you know, the equations satisfied by T are the old equation satisfied by S, and two new equations, namely Sx equals A and Sy equals B. Yes? Now, you know, the old equation is actually contained in the ideal of these two, so we don't need it. Yeah, in general, we might have to leave. When I do it later, we'll usually have to leave in the old equations. So these are called unprojection equations. S is unprojection variable, and these are unprojection equations. Yeah. So this is very familiar. If any, you know, most of you will have at some point come across Castelnuova's contractibility criterion, and so to prove Castelnuova's contractibility criterion, you write down exactly a linear system like this, consisting of things with poles along L. So from an algebraic point of view, if I was working with this as an affine equation, so if I was working with the affine cone over S3, what this is doing is throwing the divisor x equals y equals 0 to a point at infinity. Yes? And so this t contains the point 0, 0, 0, 0, 1, the point PS, where s is not 0, everybody else is 0. And this thing here says t is non-singular at PS. Yeah, and so, you know, and we get the line by the tangent plane at the point T. So, you know, this is a sort of straightforward construction. Everybody's seen it. However, the algebra of writing down hypersurface here and deducing that I've got this rational form with a pole, homogeneous rational form with a pole, and that defines a new variety and a new embedding and all the equations and so on, it doesn't depend on it being a cubic surface. This is these equations work, you know, in complete generality. X, Y, A, B can be, you know, some kind of arbitrary indeterminates and so on, and the equations still work. So in particular, if I take this guy and I assume that he contains P of 1, 2, 3, right, with given by x1 equals x2 equals 0, right, then x is given by, you know, maybe I'll use the same letters, b x1 minus a x2, right, and now who are a and b? So they're arbitrary forms of degree 6. Yes, and so I can write down a new y. So it so happens this is a 6, 6 in weighted projective space 1, 1, 1, 2, 3, 5. Right, where this 5 here is this new s, a over x1, b over x2. Yeah, so this is degree 5 with a nice clean pole along the divisor. Yes, and so he's defining, you know, here is, so you want to think of the y as being in this projective space with including the s, and the x as being here without the s, and you want to think of this as being simple linear projection that omits s, yes, and you know, the projection restricted go y to x. You expect, so this contains the point ps, same as before, and this is given by sx1 equals a, sx2 equals b, yeah, and so this is an orbifold. This is quasi-smooth points. x1 and x2 are implicit functions of the other variables. This is an orbifold point of type 1/5 of 1, 2, 3. Yes, with orbinates x3, y, and z. Yes, so you know, it's this picture here is sort of quite naive. Here I've got some kind of algebraic setup involving an s, and then I'm eliminating s. I'm writing down all the equations that don't involve s. Yes. However, this is also an operation of Murray theory. So the quotient singularity, the orbifold point, 1 over r of 1a, r minus a, has a uniquely defined thing called the Kawamata blow-up, which is the, so if I call these UVW, it's the weighted blow-up with weights UV 1A r minus a. Yes, and so what I'm doing here is I've got y, I've got this point on it, which is a point of this type, and I'm doing y1. So this is the weighted, and this one contains weighted projective space 1a r minus a. So this is the exceptional locus. The construction is locally toric. This is a weighted blob. I'm just taking the barycentric subdivision. There's a picture like this. Which is familiar, for example, from Alvaro's thesis. So the point about this is that when I do phi upper star of ky, so with the usual thing, reminder that this is a Q-Cartier divisor, I can write k of y1 equals phi upper star of k of y plus 1 over r times e. So in other words, this e that comes out here has got the smallest possible discrepancy. So when I was talking about the Murray program there, over there, then I had this notion of extremal contraction. So this is contracting an extremal ray, and this one happens to be divisorial. This takes the surface E and it contracts it down to this point. The y1 still has a 1 over a and a 1 over r minus a orbifold points. Yes? And it's a theorem, a rather easy theorem, that any extremal contraction that is not an isomorphism over y is necessarily this Karmata blow-up, this weighted blow-up. Yes? And so this forms a key step. If I want to do some birational transformation between two different Fano threefolds, or from a Fano threefold to anything else, then if I want to do anything that in any way is not an isomorphism in the neighborhood of this point, this is the only starting point. Yes? And so what's happening here is, I said this is a simple-minded procedure. I'm just projecting away. I'm doing exactly what, Del Pezzo and the Italian guys were doing in the 1890s. Yes? But this is also this kind of more sophisticated thing that I'm taking the y, I'm doing this y1, which is this, very kind of biregularly determined operation, weighted blow-up, and then I'm doing this map to x, and this is a anti-canonical embedding. Not embedding, morphism. Yes? So you might, this guy here contains P123 in this case, right? And this is going to map to P123 here. And so what do you think this map is going to be? So it's got to be, it's not contracting any divisors, so it's an isomorphism in codimension 1. Yes? However, if you think about it, this equation of x, this is certainly singular. Yes? So the A6 certainly not quasi-smooth. The fact that X7 contains this plane means that the X cannot be factorial. Yes, it has a plane there which is not a multiple of the hyperplane section. And so therefore this is not, and also you can just see, look at this, where A6 equals B6 equals 0, so A6 equals B6 equals 0 in P123 is 6 times 6 divided by 2 times 3, 6 points, right? Usually nodes. Yes? So the thing we expect to see here is that the X contains this plane, a weighted plane, and the X, as a consequence, must have these, in this case, 6 ordinary double points. Yes? So the ordinary double points, for example, if I was thinking of the Milnor fiber of X, the next, the non-singular neighbor of X, then when I go into X, and then I'm contracting 6 vanishing cycles corresponding to these nodes, and here I'm blowing them up. So this is what the physicists call a conifold transition. I'm going from a non-singular neighbor here to this variety Y, and I've certainly changed the topology. And so here this is a flopping contraction. Right? It contracts, in this case, I'm assuming everything is general, it contracts 6 copies of P1 with normal bundle -1, -1. Yes? So this is a model for unprojection. This is you know, the simple example that you should bear in mind. So I'm going to talk about the unprojection theorem, you know, which is a straightforward piece of commutative algebra, and you know, it's but you know, if you get lost in the algebra, just think about the example. So the theorem is about one Gorenstein scheme contained in another Gorenstein scheme as a in codimension 1. Right. So this is unprojection theorem. And I want to state first local version. So you know, if you're working, if you're trying to prove something, if you're trying to prove something that involves commutative algebra, you should think of local regular as being, you know, the best starting point. So here, what I want to do is suppose that I've got x and d, two local schemes. Yes, so you know, it just means there's a local ring OX and OD. Yeah, these are local rings. So I'm assuming that both are Gorenstein and the codimension D in X is 1. Yes, so I want to study HOM on the local rings, HOM on the level of sheaf of HOMs. So I want to write HOM ID into omega x. So you know, this is a kind of little motto in commutative algebra. If you're HOMing, you should HOM into omega. Yes, that's what omega is for. Yes, so we're given that omega x is OX. So there's no difference between saying omega x and OX, except that omega x has different kind of functoriality. Yes. You know, what do I want to do with this? What I want to do is say that omega d is x1 of OD into omega x. Yes. So this is just the properties of Serre-Grothendieck duality. Yes. So you know, probably a lot of you think that the dualizing sheaf is something to do with differential forms. So you can work with it sometimes if you're nice and non-singular and so on, but these are schemes, and there are no assumptions other than what I say here. The Gorenstein assumes that we're Noetherian, but apart from that, there are no assumptions at all. Yes? So what is this x1? So the x1 means this. Write down ID maps to OX maps to OD. Yes? And I want to do HOM of all of that into omega. So apply the functor omega, HOM omega to this exact sequence. So I get HOM OD into omega x. Yeah. So this is 0. Then I get HOM OX into omega x. this is omega x. I'm doing nothing at all there, right? And then finally I'm getting to this Hom I d omega x, right? And that's the thing I'm talking about. Yes, and then this goes on to x1 OD omega x, and this one is omega d, right? And then the next one is x1 of free things to a free module to free module, so this is 0. Yes. So in other words, we know that omega x is isomorphic to OX. Yes, and so I've got this isomorphism of omega x. I've got omega x is included in this thing, which I can write omega x of d. Right. So these are, if these were divisorial or even local, divisorial on some open set, then this would be a divisorial sheaf. I would talk about something which is sections of the dualizing sheaf with poles on D. And then I'm taking that and I'm mapping this to omega D. So this map is called Poincaré residue. Yes? And this one here is isomorphic to OD. Yes? So I can find some element in there, let me write S bar, for a basis. Yes? So this is something in omega D, which is isomorphic to OD, so I've chosen the basis. Right? And so this map is surjective, so I can choose, so, this one is OX, so I can choose 1 in there, and then I've got S here that maps to S bar. Yeah? So omega x of D is is generated by 1 and S with S bar in omega D a basis. Yes? And so the theorem is this, that I'm going to define OY to be equal to OX adjoined S, and then divided out by equations, S times Fi equals Gi. Right? So, so here I've got S in there, so S is a homomorphism from ID to omega x, which is isomorphic to OX, right? So this guy here is generated by Fi. Yes, and the Fi here, S of Fi, is Gi. Yeah, so the Fi and the Gi are just elements of OX. So they're exactly the same as these A and B, right? I'm writing down something which has, I'm writing down this S here, which has the perfect pole on D. So saying that S maps down to a basis of OD is saying it has the best possible pole. It's a basis, any element in here is a multiple of S plus something that comes from there. Yeah, and the S satisfies this. Yes, so what I'm doing here is X, which remember I was thinking of the X as being local. Here is Y, so the Y is contained in A1 with coordinate S over X. Yes? I'm just taking spec of this ring will just be OX, affine, one-dimensional affine space over OX. yes? And the y is the graph of S. Right? S is a if I make all these identifications of omega x with OX and so on, then S is a rational function on X, yes? And it's exactly the thing that with poles on D. So it's throwing the D away to infinity. Throws D to a point at infinity. Yeah. So this is now unprojection theorem. It's originally due to Kustin and Miller in commutative algebra, and then Papadakis and Reid about 10 years later. But our treatment's much slicker. Yes, and the y is. So the y is no longer, not necessarily and usually not local, but it's still Lorentz-Stein. Yes. So the reason it's Lorentz-Stein is, if you think of this S as a rational map, I can also think of it as a linear system on X. Yes. Namely, it's taking this thing here, which is its ideal of denominators, to an ideal of numerators here. And the ideals are isomorphic as ideals, and therefore they have isomorphic resolutions. If I set S equals 0 here, I'm giving a very rough proof. If I set S equals 0 here, then I'm just doing the ideal of denominators of X rather than the ideal of numerators. Yes? Anyway, this is a theorem. It's been in the print now for about 15 years. Stavros Papadakis has written about 20 papers with unprojection in the title. Okay, so the example I'm rubbing off is going from a hypersurface to codimension 2. I want to say I can also go from codimension 2 to codimension 3, and from codimension 3 to codimension 4. Yeah. So maybe I'll leave some of it till tomorrow, but let me do just this one case that explains something. I had a really cute example written out. I'm not going to be able to find. Oh, yes. So let's look at X, 7, 8 contained in P5, 1, 1, 2, 3, 4, 5. Yes. So this is, I mean, I hope you've all got used to this. This is 1, 2, 3, 4, 5, 6, so it's 5-dimensional. This has got 5, 9, 12, 14, 15, 16. 16 minus 15 is 1, so, this is minus 16 plus 15 is minus 1, so this is Fano, and, you have to worry about how singular it is and so on, and you'll find that it's a nice, okay, I want this to contain P of 1, 1, 4, right, so I want it to contain, let me, X, Y, Z, T, U, V. Let me, this is P114, X, Y, and V. And so this is, inside here, inside this P5, this is the codimension 3 complete intersection given by Z equals T equals V. Yes? So I have something that's codimension 2 complete intersection that contains something which is a codimension 3 complete intersection. So this theorem, so I told you the local version, there's also a projective version. And I'm just going to let the examples suffice for that. Yes. So here I was telling you, you throw the divisor D to a point at infinity. In the projective version, that's actually a point of space. Yes? So, question, how to ensure P114 contained in X78? Yeah? So let's call this F7 equals G8 equals 0. Yes? So obviously I want that F7 and G8 are in the ideal ZTB. Right? And the way to get that is to write F7 and G8 as a vector. Write it as A5, B4, C3, D6, E5, times ZTV. Yes? Oh, good. I changed my notation from the page to the blackboard. Okay, so the point is that we know how to solve these equations. So, what do I want to say? So imagine that somebody gives you 3 unknowns and 2 equations, saying these 2 equations which are inhomogeneous linear equations. Yes? So this says that the ZTV, they say that some constant, some scalar times ZTV is equal to, what do I want to say? Oh, yeah, okay, this goes to 0. So I want to say that, okay, these are homogeneous linear equations. We're working inside the function field of X or the functions on X, right? So this is wedge 2 of that matrix, A, B, C, D, E, F. This is Kramer's law. Yes? And so this says, write S times Z is B4 F3 minus C2 E5. Yes? And so, you know, this is, the only thing I'm doing here is making explicit what is this S. Yes? So, you know, I'm thinking dualizing sheaf and so on, but you can also think differential forms, or you can think projective resolutions and calculate the X explicitly, right? So I'm going to rewrite these equations. I'm going to write A, B, C, D, E, F, V minus T, Z, and S. Yes? This is a 5 by 5 skew matrix. Yes? So when I'm writing a skew matrix, I am not writing the diagonal entries. So this entry is M12, right? This entry is M23, and this one's M45. Yes, and the zeros, there are zeros down the diagonal, and there's the antisymmetric elements that you can write down for yourself if you're interested. Yes, and so I'm going to write down it has 5 diagonal Pfaffians. Yeah, so Pfaffian means MIJMKL minus MIKMJL plus MILMKJ. Yeah. So let's start by writing down the ones that don't involve S. Right. So if I cancel that line, I'm supposed to write down D times Z minus E times minus T, and then plus V times F. So I'm writing down D times Z plus E times T plus F times V equals, yes? And then if I cancel the second row, I'm supposed to write down A times Z plus B times, so minus B times minus T, right, plus C times V. Yeah, and that's exactly these two equations. Right, these are the equations that say that the plane is contained in the threefold. Yes, and then there are 3 new equations, and the 3 new equations say that S times V equals AE minus BD. Yes, and that's exactly these equations. It's saying that S times Z and T and V in turn are the 2 by 2 minus of this matrix. Right. So this says we go to Y inside P of 1, 1, 2, 3, 3, 4, 5. I'm sorry, 3, 4, 4, 5. Right, where this is the new variable S, and everything else. So I keep the old equations, and I add 3 new equations. Right, so I have an unprojection variable, which is the new guy S, and then I have 3 equations saying that it vanishes on this complete intersection ideal. So, sorry, it multiplies the complete intersection ideal into homogeneous forms. So that's into this omega X. Yeah. So the red light is on. So this will be my starting point for Tom and Jerry. Yes, I want to do this again. I told you this kind of motto: if you enjoyed doing something, you should do it again. So I want to go from this codimension 3 guy, that I just constructed, to codimension 4. And that's the place where I tell you it's not straightforward, right? If you want a codimension 3 ideal, codimension 2 ideal to be, a codimension 2 complete intersection to contain a codimension 3 complete intersection, there's no choice at all. You've got to do this. On the other hand, if I want a Pfaffian, a variety defined by Pfaffians, there are non-trivial syzygies here. This matrix tells you the equations, and it also tells you the syzygies on it. If I want this thing to contain a codimension 4 complete intersection, there are lots of choices. So there are 10 Jerrys and 5 Toms. So I'll explain this next time. And these give rise to several different solutions to the problem of finding the codimension 4 guy that lies above this one.